Okay. So last week we have shown that a regular string variable operator is self as a joint. Okay. So that is with respect to any waiting function of x. Okay. So we will utilize this property to prove several important results. All right. Okay, so the first results will be stated in this theorem. So eigenvalues of a regular string variable operator non-degenerate, which means that there is a unique eigenfunction okay, up to a constant. Alright, so let's prove this result. So we let 1 sub 1 and 1 sub 2 be eigen functions, okay, of regular string variable operator L, okay, corresponding to a given eigenvalue. Alright, say lambda. And so by definition of eigenfunction and eigenvalue, we know that L1, so L operator on L1 will be lambda times Y1, and L operator on Y2 is lambda times Y2. Okay, so that is the definition of eigenvalue and eigenfunctions. Okay. Alright, so now we actually will multiply this equation by Y2 and multiply this equation by Y1. Okay, so Y2 L Y1 equal to lambda Y1 Y2, and this is equal to Y1 times L Y2. Okay, so this is implies that Y2 times L of Y1, minus Y1 times L of Y2 is equal to 0. Right, and now we will substitute the regular string variable operator L. Okay, from our definition in last week. So this will imply that so Y2 and minus okay. okay, of x, right, and here is minus p of x, 1 prime, minus q of x of y1, okay, this one, and minus y1 and 1 over x, okay, oh, by the way, we may times r, okay, equal to 0. Alright, so we can delete this one. To simplify the derivation, so this is minus p of x y1 prime minus q of x y1. Okay, and minus y1 minus p of x y2 prime minus q of x y2 equal to 0. Okay. Any questions? So just multiply with r. Okay. So remember that of u, we call that u1 over rx minus p over u prime minus q of x u. Okay, this is the operator. So when we multiply of x, remember for a regular singular problem, the function are always positive. Okay, always positive. All right, and so we look at the difference here. Alright, so this is implies that. So when we multiply, you can see this term. This is q of x, 1 over 2, minus sign. But minus becomes plus sign, and we have q of x, 1 over 2, so they can be cancelled. And so we have that. So we have that p of x y1 prime is equal to p of x y2 prime. All right? Okay, is that correct? Oh, sorry, this is y2, right, and minus y1 equal to 0. Yep. Okay, so this two times this one. And minus sign here. Okay. Now, so we So when we do px O2 px prime O1 prime plus p of x O1 double prime minus y1 p prime of x y2 prime plus p of x y2 double prime equal to 0. Right. And so p prime of x, so you can write down p prime of x, and here is y1 prime, y2, okay, minus y1, y2 prime, plus p of x, y2, y1 double prime, and y2 minus y1, y2 double prime equal to 0. Okay, and that we can write down p of x and y1 prime, y2 minus y1 and the prime and the prime. The reason is that we can okay, then we write it down, p of x, okay, y1 prime, y2, write p of x, and here, plus, minus, minus y1. Okay, so we add one term but substitute the same term. Okay, and this one will be y1 prime, y2 minus y1, y2 prime. Okay, because that the prime of this product term is equal to the sum of these two terms. Okay, and the prime of this product terms is equal to the sum of these two terms. Okay, so that we get p of x and y1 prime y2 minus y1 prime equal to 0. Okay, so that is the alright, so by integration, because this is the due is 0, so which means that p of x and the determinant of y1, y2, y1 prime, y2 prime, okay, is equal to c, a constant, okay, for all x in AB in the course of interval, so we may think about this is a constant. And what is this? This is the Wronskian, right? Of 1 and 1, 2, right? So this means that where y1x right is the Wronskian of y1 and y2. Okay, right. So this is the Wronskian. Now since both y1 and y2, as we know that y1 and y2 are from the vector space V, right? And because of the operator, so we know the operator is from V to V2. Okay, and as we define the vector space V, every member in V satisfy the two boundary conditions. Okay? Alright, so things we want to satisfy the boundary condition. Okay, at x equal to a. Okay, so we have the Wronskian of y1 and y2 at a, which is equal to a y2 prime a minus y prime a y2 a, and is equal to 0. Okay, so the Wronskian, you know that so the value is 0, and which implies that P of x and the W of y1, y2 of x is 0. Okay, because when we evaluate, because this is a constant, right? And we let x equal to a here, okay, a here, but the Wronskian at a is 0. The Wronskian is 0. So that means that this is 0 for all x in a, b. Okay, and again, because p of x is assumed to be positive in all regular problem, so this implies that the Wronskian v equals 0 for all x in so in all regular problem, p of x always positive. Okay, and so the Wronskian is 0. And when we study the ordinary differential equations, that we have the Wronskian of two functions to be 0, which means that they are linearly dependent. Okay, well, because since both y1 and Y2 are solutions of a homogeneous, because that each eigen equation gives us a homogeneous, so that R is a solution of a homogeneous second order ordinary differential equation. So this is a homogeneous linear second order ODE with continuous coefficient AB. Okay, because then we have standard equations. Standard equations, okay, it's a homogeneous linear, okay, homogeneous linear second order ODE with continuous coefficients, okay, so that Y1 and Y2 are linearly dependent function. As AB. Okay. So that Y2 x must be equal to C11x. Okay, for all x in AB, for some non-zero constant C. Alright, so this is the end proof. Okay. Alright, so the idea is to use the property we learned from an ordinary differential equation. Okay? Yeah. I'm sorry? Because we know P of x times Wronskian is a constant, right? And when we, for all x in this interval, we just verify what is the constant by evaluate this function at x equal to a. Yeah. So when x equal to a, right? So this is constant, right? So P of a Wronskian Y1 Y2 a is a constant. It's a constant, right? But this is equal to 0. This is always positive, right? So P of a is a positive number, but the Wronskian is 0. Why? Because when Wronskian is this difference, and we know Y1, Y2 satisfy the boundary conditions we have. Okay, the boundary condition we have. Right. What are our boundary conditions? Well, the boundary conditions are okay. Actually, we use that when we derive Lagrange identities. So, all right, the boundary conditions. Okay, let me see. K1. And A1. Right. So Y1 and Y2 satisfy these two boundary conditions. Okay. The boundary conditions refer to this one. Okay. Now, so we use just the first one, right? Here's the first one. So the first one tells us that, so which implies K1 Y1 A plus K2 Y2 A equals 0. And K1 Y2A plus K2 Y2A equals 0, right? So both of Y1 and Y2 satisfy the first boundary condition. So it's this one. So now this is a system of linear equations, right? With unknowns, so we can write it down. I'm sorry. Okay, Y1 prime. So Y1 prime A. And here we have Y2A, Y2 prime of A. Sorry about that. Okay. This is equal to 0, 0. Right? So that these two linear equations is equivalent to this matrix equations. And we know K1, K2 is a non-zero vector because at least one of K1 and K2 must be non-zero, right? By our assumption. So this is non-zero. This is non-zero, right? So K1, K2 is a solution of this equation. And since K1, K2 is not equal to 0, 0, this implies this matrix is invertible. Why? Because if this matrix is non-invertible, the reason is if it's invertible, then K1, K2 must be 0. Right? So this implies that the determinant of Y1A, Y1 prime of A, Y2A, Y2 prime of A must equal to 0 because it's not invertible. So the determinant is 0. And the determinant is 0 means what is the determinant of this matrix? Just this one, right? So this is the determinant. This is equal to the determinant. Okay, so this is the determinant. And the determinant is 0, so that it must be 0.
What do you mean continuous coefficients?
Oh, the continuous coefficients, remember our Steinberg problem. Okay. Okay, continuous with continuous coefficient. Because the coefficient of the Steinberg problem are functions, okay? So that, right, the below u, okay, u, okay, this is equal to, as we know, this is R of x minus p of x u prime minus q of x u equal to lambda u. Okay, and so this is equal to p of x u prime plus q of x plus lambda r of x equal to 0. Okay, if you go down, you have u to the prime plus p prime u prime plus So now it's a second order differential equation, right? Ordinary differential equation is linear, right? Because you can see that there is no linear terms of the unknown functions. And the coefficient, this is the coefficient of the second order term here, and this is the coefficient of the first order term, and this is the coefficient. So we have three coefficients here. And by our assumption, P, Q, R are all continuous functions. Okay? So these three coefficients functions are continuous functions. This is why we have continuous coefficients. Oh yeah, we assume at the beginning of this section, we assume P prime, Q, and R. These four functions are continuous functions. And we further assume P and R are positive functions. Okay? So we have two. So if you recall, yeah.
These solutions are functions from where to where?
Oh, we restrict the domain of this linear transformation linear operator from V. Yeah. Yeah, V is a subspace of L2, and we specify, right? Yeah.
Functions from A to B, closed interval to
Yeah, functions. Yeah. Opposite to C.
C. Which differentiation is this? There are two differentiations.
That's fine, because the real part and the imaginary part, right? So both of the part can be differentiated.
So it's not the differentiation defined on complex field.
No, because our variable x is they are real variables. They just have complex value, but the defining variable, the domain, is the interval from A to B. By the way, the coefficients here are real continuous R, P, and Q. They are assumed to be real valued. Okay. It's very important to assume that the P or Q are reals. Why? Because it is needed to show that the string of the operator L is self-adjoint, as we proved last week. Okay, so it's very important that the coefficient here are reals, even though the unknown function U can be complex valued. Okay, but you can even think about that. You consider real part and imaginary part. So both of the real part and imaginary part of U must satisfy the same stem behavior differential equation. Okay. So other questions about proof here? Right. So the idea to show that two eigenfunctions corresponding to the same eigenvalues are basically unique, right, up to a constant, means that these two eigenfunctions must be linearly dependent to each other, which shows that here that y2 must be a non-zero constant times y1. Okay, and to show that, we use Wronskian, the property of Wronskian of two functions we learned in ODE. Okay, you know Wronskian of n functions can be defined, right? If we have n functions, the Wronskian of the n functions is an n by n matrix. Okay, so biometrics. Okay. Okay, so one value, so that to show two function linearly dependent is to show that Roskin is zero function, right? Zero function, not only is zero for all x in AB. Okay, and these two functions must be solutions of the same homogeneous linear ODE with constant coefficients. Okay. Okay, and we should refer back to last semester when we learned ODE there. Any questions around the proof? Okay, so we know that the first result tells us that for a regular stem-Liouville operator, so this is a very important regular, only for regular. For a regular stem-Liouville operator, corresponding to each eigenvalue, there is one unique eigenfunctions. Okay, it makes up to a constant. Okay, so any two eigenfunctions should be linearly dependent to each other. This is called non-degeneracy of eigenvalue. Okay, if you register linear algebra class this semester, you will soon to consider eigenvalue problems of linear operators. I don't think. Did you? I'm not so sure because this week is, I think, is the first week. Yeah, the first week of the semester. Yeah, it's probably you are already first week eigenvalue problem in the algebra course. Do you know? Not yet. Okay, just still considering vector space already, not yet to linear operators. Okay. Okay, so maybe sooner or later, probably 2 or 3 weeks later, you will face up with the same problem like us, the eigenvalue problem there. Okay? Alright, so this is the first consequence we have. The second one, any eigenvalue of a regular string Liouville operator if it exists, alright, is a real number. Okay. Alright, so again, this is a property of a self-adjoint linear operator. Alright, but we can show it now for our specific example, especially for regular stem-Liouville operator. Okay. So assume that lambda is an eigenvalue of L, and U is an eigenfunction in V corresponding to lambda, i.e. it satisfies the following eigenequation. Okay, so we assume lambda is an eigenvalue. Okay. The point is, if this means that for a linear operator, it may not have any eigenvalue. It may not have. Okay. But for this linear operator, for this regular standard operator L, if an eigenvalue exists, then it must be a real number. Okay. So we suppose we have such an eigenequation. So lambda is an eigenvalue and U is a corresponding eigenfunction. Remember, any eigenfunction should be non-zero by definition. Okay? Why? Because L0 equal to lambda 0. 0 always a solution of any homogeneous linear ODE. Okay? So, okay. Alright. Now, since L is self-adjoint, V with respect to the weighting function of X by theorem 11.5.8. So we know that LU must be equal to U and LU. Okay? Right, so this inner product must be with this inner product. Okay. Alright, so this implies that by the eigenequation, this is lambda U equal to U lambda U here. Okay. Now the inner product is linear for the first argument, so this is equal to, and lambda bar, but it's conjugate linear for the second argument, so lambda bar in here. Okay, so we have that. Now, since U is a non-zero continuous function, right? Since U is a non-zero continuous function, because remember in capital V, subspace, every function in this subspace has continuous derivative. So of course, this function must be continuous. So U is a continuous and a non-zero function. So that this inner product must be non-zero. Okay, must be non-zero. must be non-zero. So this is implies that. Okay, so we have, lambda minus lambda bar times u equal to 0. Now, this inner product is non-zero, so which means that lambda minus lambda bar is 0, which means lambda equal to lambda bar, i.e. lambda is real. Okay? Any questions? Right. Now, up to now, we haven't answered yet that is there any eigenvalue for a regular standard operator? This theorem answer this question. So the eigenvalues of a standard linear operator from an infinite increasing sequence. Alright, so lambda 1, that's the lambda 2, lambda n. Alright, and the limit of the sequence of eigenvalue is infinite. Right, and this result, the proof of this real is a little bit involved. So I will omit here, just give you the description in this theorem. Okay. Of course, I have given a reference for you if you are interested in such a proof for you in my lecture notes. But for this theorem, we know that I'm sorry. For a regular standard operator, we have infinite many eigenvalues. Okay, right? So it started from the smallest one. We call lambda 1, right? So it has a smallest eigenvalue. Lambda 1 here, and then the others together with others they form an infinite increasing sequence, right? And the limit of lambda n is infinity. Okay, so it's going up to infinity. And combining theorems 11.5 point B and 11.5 point D. In B, we show that corresponding to each eigenvalue, there is a unique eigenfunction up to a constant. So that for each to the etc. We can select one corresponding eigenfunctions. One corresponding eigenfunction, we call it phi n, to form an eigensystem. Alright, called n from 1 to infinity. Alright, so for each eigenvalue number n, we just select one corresponding function called phi n, and we form an eigensystem. So this eigensystem consists of an even number of functions. Okay, even number of functions there.
Why do we have the smallest eigenvalue?
I'm sorry?
Why do we have the smallest eigenvalue?
Oh, why? Why do we have a smallest eigenvalue here? Right. If I give you a very quick and simple, it's the nature of a regular Sturm-Liouville operator. Yeah, it's a nature for them. And I think the important thing is that eigenvalue will tend to infinity.
And why are they countable?
Well, because of we are talking about functions on a finite closed interval. Okay. Yeah. This is a nature, okay, because we are talking about functions on finite closed interval. Yeah, because there is a terminology in linear function. This is called compact operator. Okay, so it's a nature of this operator called compact operator.
Compact doesn't mean that it's
Yeah, compact operator implies that eigenvalues are countable. Bounded operator, okay, and because there are many different kinds. For example, for unbounded linear operators, the eigenvalue may be continuous. And we have eigenvalue, for example, eigenvalue in between an interval. Every number in an interval is an eigenvalue. It's possible. For example, in quantum mechanics, for example, the so-called position operator, for example, the position operator is unbounded, and as we know, position, if one dimension, position can be any point, right, along the real line. Okay, so any number can be an eigenvalue. Alright? And because it's Hermitian, so all eigenvalues should be real. All self-adjoint. Right? So position operators are self-adjoint operators because they are observables, just like the regular Sturm-Liouville operator is a self-adjoint operator. So we just prove here any regular, because this is we use the self-adjoint property. So any eigenvalue of a self-adjoint must be real. And the position can be any point, so it's continuous. So continuous. So, and it's unbounded. It's not bounded. It's, of course, not compact. So that so I should say that because regularity of and we consider functions defined on a compact, because a finite closed interval is a compact set, okay, in the real line. Hmm? No. Okay, the finite closed interval, any finite closed interval is a compact subset. Okay, and because of that, any continuous function on a compact subset has extreme values, the maximum value and the minimum value. No. Right. Yeah. So, yeah, I think this is too far away from this course. If you, yeah. They are concepts in topology, anyway. But well, we should say that we are lucky to deal with only regular Sturm-Liouville operators, so that the eigenvalue is discrete, countable. Even though we have even many, but it's discrete, makes it uncountable, right? Even though it's infinite, but the trend of this eigenvalue will go to infinity, okay? So the eigenvalue becomes bigger and bigger there. And the important thing is that we can find an eigensystem here. And in this eigensystem, every function is an eigenfunction corresponding to an eigenvalue, okay? And corresponding to distinct eigenvalue, because they are distinct here. Now comes with the important theorem, and actually this theorem is stated in the textbook. The orthogonality of an eigensystem. So that any such an eigensystem has orthogonality. So let's state that if per Ci and per Cj are two eigenfunctions, right, of a regular Sturm-Liouville operator. Corresponding to two distinct eigenvalues lambda I and lambda j, respectively. Okay. Right. So when we pick up, this is phi, I'm sorry, phi I, pick up phi I and phi j from this eigensystem corresponding to distinct. So the important thing is that they corresponding to distinct eigenvalues, right? Number I and number j. Then the inner product, okay, with respect to that weighting function R, this inner product, all right? As we know, the definition phi I x, phi j bar x dx. This inner product must be equal to 0. Okay? Which says that phi I and phi j are orthogonal. Okay, are orthogonal with respect to the weighting function of x. And the proof, right, again, since L is self-adjoint of V with respect to the weighting function of x, so we have L of phi I, phi j. So by the property of self-adjoint operators, okay, alright, so this is for the self-adjoint property of the regular stem variable operator L here. Now, because phi I is an eigenfunction corresponding to lambda I, so this is lambda I, phi I, and phi j equal to phi I, and this is, and the phi j is an eigenvalue, eigenfunction of L corresponding to eigenvalue lambda j, so the lambda j, phi j here. And because from theorem 11.5.c, both eigenvalues lambda I and lambda j are real, okay, so this is implies lambda I, phi j equal to lambda j, phi j here. Okay, and so this lambda I minus lambda j, phi j equal to 0. Now, because lambda I and lambda j are distinct eigenvalues, so this is non-zero. So this is implies that the inner product of phi I and phi j with respect to the weighting function R, it must be 0. Okay. So this proves this result. So they are, so you see that there are infinitely many regular stem variable operators. There are even many. Okay, and for each regular stem variable operator, we can construct an eigensystem. And by this theorem, any eigensystem is orthogonal. Okay, so actually we construct a sequence of orthogonal functions. Okay, and the orthogonality should be accounted with respect to a weighting function R. Okay, because this R is associated with the corresponding regular stem variable operator. Okay, so you should know that. Okay. Yes?
Why are they infinite and countable, and why do they have
Okay. Okay, yeah. At this point, I can just answer your questions to say that because the regular Stendiovia operator is a compact operator. Yeah. And if you want to know the answer, you have to refer to any linear function textbook. Okay. I give you I give you a reference to see a proof of the theorem in the lecture notes. So you can look at, go to see. I think it's. Okay. And the reference here. Yeah. Okay, it's a textbook about ordinary differential equation. Of course, this is more involved than the content you learn from last semester. Okay, but if you can still. But it's a property of compact linear operator. Okay.
So compact linear operator is the linear operator which operates on a compact set.
No. It has its definition, but I can't say it right now because it out of the scope of this course. So if you are interested, you can just refer to you can do maybe I will give you a good reference.
Which would be
Okay, auto reading has a very good textbook on functional analysis. What?
which would have three reads, right? 有定不是有三本
The title is the functional analysis. Alright? And so see context compact operator. Okay. And specifically, I will give you reference set, to point out this theorem in a textbook on the theory of ordinary differential equations. Okay, so let's take a break up to 12:40. All right.
最大的就是一定有三本，它是最后就是俗称叫它。
对啊，你就 Okay. Right. Alright, so an eigenvalue phi n corresponding to an an eigenfunction phi n corresponding to an eigenvalue lambda n of a regular standard operator is called normalized. So it's called normalized with respect to the weighting function of x if the inner product of phi n is itself, right? Of course, with respect to the weighting function, right? So this inner product becomes to be is equal to 1. Right. So in this case, the eigensystem, right, is called also normal eigensystem. Of the regular stem, there will be a problem on AB or operator. That's fine. And for any function in R2, okay, which means that f is a square integrable function defined on the finite cosine interval AB. Okay. The series summation of Cn phi n x with Cn equal to the inner product, okay, of the function f with the nth eigenfunction, normalize the eigenfunction here. So is called the regular generalized Fourier series generated by f with respect to the orthonormal eigen system. Okay, so now, just like in the trigonometric eigen system, which consists of constant function 1, sin x, cosine x, cosine x, sin x, cosine 2x, sin 2x, etc., cosine nx, sin nx, etc., right? So then we construct a trigonometric Fourier series generated by f, and now for any square integrable function here, we can construct similar series, okay, here, and the coefficients is actually the inner product of the function f with the nth eigenfunction here, okay, and so that you can see this is just like a projection of the square integrable function to the direction represented by the nth eigenfunction. Okay, as we know that is an orthonormal basis for R3, so we know and the three unit vectors, right? Each of them has unit length, so it's normalized. And any two of them are orthogonal to each other because their inner product is 0 here. Okay, and the projection, so a vector has, so a vector in 3 has A is the inner product, so this is E1, E2, E3, so it's E1, and B is E2, and the C is E3. Okay. So the inner product of V and the E1 give us A. So A is the projection, okay, for the vector V onto the x coordinate. All right, and B is the projection, the component, right? The component of V to the y coordinate, and C is the projection of the vector V to the z. E3 is on the z-axis. Okay. So that the eigens, the also normal eigensystem corresponding to an orthonormal basis for R3. Okay, you can see that. Okay. So from that we can reconstruct. We know this is A, E1 plus B, E2 plus C, E3. Okay, so the vector can be reconstructed by using the basis vectors here with their component, projection component. So this is A, E1, B, E2, and C, E3. And so the projection, you see, the Cn is just the projection of the function. So function can be regarded as a vector and project to the direction determined by the nth eigenfunction. Okay, just like so phi n is just like a EI here. Okay, and this inner product gives us the projection component. And the reconstruction is that here, that we use the projection multiply with the direction, right, defined here, and give us a sum. Now, in here, it's simple because we are considering finite dimensional vector space, okay? So this is 3-dimensional only. So the sum has only 3 terms, simple. But we are considering infinite dimensional inner product space, okay? And it has a corresponding also normal eigensystem. In this system, we have infinite many normalized vectors here. Okay, so the question becomes more involved because it's a series of functions. And again, you have asked, you will have the question 1, convergence problem. Does this series converge? Second, the representation problem. If it converge, does the limit equal to the f? So now we have 2 problems again. Okay, the same 2 problems as we asked in the first section of this chapter. Okay, in that we consider trigonometric Fourier series. But this time, we consider generalized Fourier series because the eigenfunction may not be sinusoidal, right? May not be sinusoidal functions, can be different, much different functions there. Okay. So anyway, we can construct a series. Alright, so now the following theorem answers the convergence and the representation problems of regular general, that is the Fourier series. And of course this theorem is very general, so the proof is involved. Again, I just state the result without give a proof, so that we can represent tension theorem of regular general, that is the Fourier series. Right. So let F be piecewise continuous. continuous on AB. All right, because it is piecewise continuous, so of course F is in L2, as we have shown before. So it can generalize any regular generalized Fourier series. Okay. And have a piecewise continuous derivative. On AB. Alright, and I describe what do you mean that a piecewise continuous function has a piecewise continuous derivative. Okay? Right, so 1. The generalized Fourier series and from 1 to infinity Cn times phi nx, okay, generated by f with respect to orthonormal eigensystem phi n of regular stem linear operator on AB will converge to, will converge to half of the left hand and the right hand limit of f at x, right, at each point x in the open interval. In the open interval. Okay? This is the first one. The second result is that now at the endpoint, alright, because it converges to this wherever x in the open interval. How about the endpoint? So at the endpoint, x equal to a. Oh, I forgot to put the regular. So the regular generalize. I forgot. The regular generalized Fourier series Cn phi converges to f of a plus if k2 is not equal to 0. Okay. And the boundary condition conditions. Right? K1, K2, and suppose K2 is non-zero. Okay? K2 non-zero. If this is non-zero, then this is series. When x equal to the endpoint x equal to a, then this series converges to the right-hand limit. Okay, the limit of f. So if this boundary condition is not zero, and to 0 if k2 equal to 0. Why? Because if k2 is 0, now k1 not 0, so ua equals 0, right? ua equals 0. So any solution of the Rickerson-Beerville equation must satisfy this boundary ua equals 0. Every eigen, because in the eigen system, every phi n satisfies boundary conditions. Remember that? So phi n a equal to 0. Phi n a equals 0. So if you do the substitution x equal to a, then phi n a must be 0. So the sum must be 0. Okay? So that's why it's go to 0 without any doubt. Okay, if k2 is 0, because k1 is non-zero, means that phi n a should be 0 for all n. But if k2 not equal to 0, if k2 not equal to 0 here, then you know that you have for a combination to be 0. So that the phi n a may not be 0. Right? May not be 0. So you have the opportunity for this series sum converge to the right-hand limit of f at x equal to a. Okay, so that's why this is because the boundary condition, because phi on every eigenfunction should satisfy boundary condition. Okay, so boundary condition is the hard condition you should have. Okay, so that is this one. This is about at the endpoint. And at the endpoint b, x equal to b, the regular generalized Fourier series Cn minus x converges to f of b minus the left-hand limit of f at x equal to b if L2 is not 0. In the boundary condition. Okay, and to 0 if L2 is 0. Why? Because if F2 is 0, then phi n b should be 0 for all n. Okay, and so they go to 0 because of so if L2 is 0, now L1 is non-zero, so UB must be equal to 0. And every phi n, satisfy the boundary conditions. So we have that. Okay, so the first part gives us the answer the convergence problem, which goes to this quantity, for all point x in the interior of this interval. Okay, but at two endpoints you have to see what is the boundary condition. Okay, so what is boundary condition to have? Right, third part, if f is also continuous on a finite cost interval with is less than C and D is less than B. All right. So this finite cost interval is inside of the defined interval if it's inside. And if f is also continuous, then this series, then this regular generalized first series converge to f uniformly and absolutely on CD. Okay. Or if f is also continuous on AD. So, right, on AD with right, so B is less than B, but the endpoint of this interval is the endpoint of the defining interval AB. And FA equal to 0 if K2 is 0, right? So that the same way, so that if K2 is 0, so that phi and A must be 0, right? Or in this case, then this series converges to F uniformly and absolutely. On the whole interval. And finally, the similar result, or if f is also continuous on CB with A, B, and FB equal to 0 if L2 is equal to 0. So that phi and B is 0. Then summation. So then the regular generalized for theories converges to F uniformly and absolutely on CB. Okay. So there are 5 points. The first 2 points corresponding to the pointwise convergence problem, okay, of the regular generalized Fourier series. Okay. But the last 3 points corresponding to uniform convergence of the regular generalized Fourier series. Okay, so you will see that. Personally, I think the theorem answer our questions about convergence and representation, and it is useful in practice. Why? Because that usually, especially in electrical engineering, that we encounter the signal F to be piecewise continuous and has piecewise continuous derivative. It's quite often to have. Okay, so the theorem is quite enough for us as an engineer. Okay. Any questions? And you remember that I took 2 examples. So these 2 examples corresponding to regular standard operators. And you can see the first example gives us eigensystem of sine functions, right? Just only sine functions. The second example, gives us eigensystem of cosine function, including 1, right? And you see these 2 eigenfunctions, of course, that they appear in our half-range representation of functions. We studied in the second sections. Okay, so they are. So the sine, the eigensystem of sine functions, and the eigensystem of cosine function, they are 2 special kind of eigens. Also, they are not memorized yet, right? They are not, but they are also orthogonal eigensystem. But you can memorize them. Okay. And the working function, the R is what? The constant one. Okay, very particular one. But remember, at the beginning, we have a trigonometry with eigensystem, which consisting of cosine and sine function, right? So you may have a question that is this eigensystem corresponding some standard problems? All right, and so we will answer this question next Thursday, all right, with different boundary conditions. Okay, so we will see that. Okay, so regular standard problem is a very big class of problem we have, but we have other relatives of these problems, like a periodic standard problem, as well as some special kinds of non-regular standard problems later on. Okay, and so we will study that on Thursday. Right, so I'll stop here. Okay, I'll see you Thursday.